Hello, viewers. Welcome to class for today. We want to look at the concept of projectiles. My students will join the class now. You can subscribe to this channel. Thank you. All right, so they're supposed to join now. Okay. Good afternoon. How are you today? All right, you're welcome to class for today. The topic we want to look at today is projectile, but before we look into that, we'll try to do a quick review of the last topic, okay? During the last class, we looked into laws of motion, Newton's laws of motion. We concluded that every object will continue to be in a state of rest or of uniform motion unless it's acted upon by an external force. And in the light of that, we discovered that if an object is moving and it suddenly stops, there will be a reluctance in that object that refuses to stop, and that is what we call inertia. Is that clear? Is that clear? Oh, I can't really seem to hear you. Can you hear me? Okay, very good. So we talked about force, and we talked about the second, law of motion that states that the rate of change in the momentum of an object is directly proportional to the applied force, and the change takes place in the direction of the force. Also, we were able to prove um, F equal to ma from the second law, and we stopped on the third law that says to every action there is an equal but opposite reaction. What did the third law state? Yeah, to every action, there is an equal but opposite reaction. And we try to, explain that when you are in a bus and you're traveling, as your bus is speeding past the forest trees, if you look out from the window, the forest trees will appear to be moving. If your bus stops, the forest trees stop. The motion of the forest trees stop. And if your bus moves slowly, they begin to move slowly. If your bus moves, the vehicle you're using, if it moves very fast, then if you look through the window of the vehicle, you will discover that the trees will appear to be moving very fast, or not only the trees, but every object. So I'm going to show you something here. I'm going to show you something on this screen here. Let me see. Let me try to show you. Can you hear me? Okay. So I want to play a video for you to support that claim about relative motion, that when an object is in motion, then as it moves past other objects, then the other objects that are not mobile or that are not moving will appear to be moving in relation to the motion of the object that is moving. Is that clear? Is that clear? Okay, so like I said, I want to show you this. Let me try to play the video and see if it works. Let's see.
Suppose you are traveling in an open car. Just for fun, you throw an apple out of it.
Okay.
Now you can observe an intriguing phenomenon.
Hold on. I want to start that again. Okay. Okay.
Suppose you are traveling in an open car. Just for fun, you throw an apple out of it. Now you can observe.
Now wait. Did you see the movement of the vehicle. As the vehicle keeps moving forward, the trees appears to be moving backward. I'm going to play it again.
Suppose you are traveling in an open car.
Did you notice that? So as the trees appears to be moving backward, the trees are not moving anyway, but the motion that you are observing, because from your eye, the trees are not stationary, because you can see them moving as you see the vehicle moving too. And if you look at the man that is seated in the open car, let me ask you a question. Is the man moving? The man was in a vehicle that was moving, right? But the man himself was not moving. But are you telling me that the man's position is not changing? His position is changing. So he is moving, but he is not really moving. But the motion of the man is in relation to the motion of the vehicle. So if the vehicle moves fast, he is moving fast, whereas he is not leaving his spot on the car. Okay, let's watch it again and see now.
Suppose you are traveling in an open car. Just for fun, you throw an apple out of it. Now you can observe an intriguing phenomenon. After hitting the road, the apple suddenly starts to follow you.
Wait, wait. After the apple hits the road, it started following the car, right? Right? Why is the apple moving? Is the apple a living thing that can move? Let's watch it again. Maybe so I want you to listen. When I finish this short clip, I will call one of you to explain to me. So listen. In fact, you could jot down anything, but just listen.
You throw an apple out of it. Now you can observe an intriguing phenomenon. After hitting the road, the apple suddenly starts to follow you. How do you explain this crazy behavior? Let's get into it. When you hold the apple inside the car, it feels like the apple is at rest. However,
Take note of what it says. It said when you hold the apple inside the car, it feels like the apple is at rest. When the man sits in the car or stands in the car, it feels like the man is at rest. Am I correct? Okay, good. Let's listen.
to the road, the apple is moving at the same speed as the car.
Now, as the if I play it now, what are the things that you will see changing position? Number one, the vehicle. Number two, the driver. Number three, the man. Number four, the apple. And number five, the trees. And number six, the geographical location is changing. Okay, watch out for all those things now.
When you hold the apple inside the car, it feels like the apple is at rest. However, relative to the road, the apple is moving at the same speed as the car.
Not only the apple, all of the objects appear to be moving at the speed of the car. If the car speeds off, with a greater speed, they would also speed off, moving with a greater speed. But if the car slows down, they would also slow down. And when the car stops, then nothing moves. Is that clear? Is that clear? Okay.
When you throw the apple from the car, you are in fact giving it a velocity opposite to its initial velocity. This opposite velocity reduces the apple's net velocity. The apple still moves in a forward direction, but with a lower velocity than the car.
Now, you threw the apple with a force. That force gives it a kind of velocity. But the velocity you have given it cannot overcome the speed of the car with which the apple appears to be moving initially. So definitely, the apple can never go backward. It will be coming forward and following you because the speed of the vehicle is greater than the speed with which you throw the apple backward. Okay? So The speed that you use to throw it backward will only try to neutralize the speed of the vehicle. Let us assume that you are able to generate the speed of the vehicle on your hand to throw the apple and it's equal, then the apple will neither move forward nor backward. It will just drop to the ground straight. But because you are using a tiny speed compared to the speed of the vehicle, so it will that speed you are using will be neutralized from the speed of the vehicle. Then it will now keep moving towards the vehicle until the speed wears out by gravity. Is that clear? Is that clear? Okay.
which means the apple will slowly move away from the car. Even after hitting the road, the apple will continue to have a forward velocity. So the apple has a forward velocity before and after hitting the road.
Listen to that. The apple has a forward velocity before hitting the road. That's when you threw it, and after hitting the road, after landing on the road. So the apple was never moving backward. But because you are moving forward at a greater speed, it will appear as if the apple is moving backward. Let me give you this scenario. You are in a vehicle, you are sitting at the front by the driver's seat. Your vehicle speed past another vehicle, and you look at that vehicle like this, it will appear as if the vehicle is going backward. It's not going backward, it's actually coming along the way where you are going. Yes or no? Yes or no? I can't hear you. Can you hear me? Oh, I don't know. Maybe what will happen is that they can check the zoom setting and try to allow background noise or use original sound under the audio settings. If you're able to use it, then I'll be able to hear even if a pin drops on the floor.
Hello, sir. They are a bit distant away from the laptop.
Yes, I'm aware.
Can you hear me?
I can hear you, sir. I'm aware.
I can hear me clearly because I'm very close to the laptop. I'll work on that.
So if we check on that audio settings and you go to the Zoom settings, the audio settings, under it, if you scroll down, there's a place that says original sound. What you're going to meet there will be something that has been suppressing their voice, because in as much as they are in that room or even in another room, I'm supposed to hear them based on that Zoom setting. Okay, so we're going to continue. Yeah.
Let's fix that now. I don't want to waste your time.
Okay.
So we go to where?
Yeah, go to Zoom settings, then audio.
Audio, okay.
Then under the audio, you can scroll down. You will see the one that is maybe the one that is checked already is the toggle to suppress background or noise or something. You will see the third one that says original sound.
You've seen original sound?
There will be
for
one
musician.
For music. Yeah, please use it. Have you clicked on that one?
I'm coming, sir.
Okay. So when you clicked, one of them should talk, then I should be able to hear clearly. If I let me try and bring my own settings up and see. Okay.
Where's original sound for me? This one, Abby.
Aha. Let them talk now. Daniel.
Hello.
Aha. That's very perfect. I can hear them now.
You can hear them now.
Yes. Yes, I can hear them. So, just hold on a second.
Or hit the road. Here comes the trick our brain plays. Until the apple hits the road, the brain analyzes the situation in reference to the car. By that frame of reference, the apple has a velocity opposite to the car, the initial velocity you gave it when you tossed it.
Make sure you concentrate, please.
so you feel like the apple is moving backward. However, after the apple hits the road, your brain analyzes the movement of the apple in reference to the ground. Here, obviously, the apple has a forward velocity, and you feel like the apple suddenly starts to follow you. In short, this interesting phenomenon happens because your brain changed its frame of reference between you tossing the apple and the apple hitting the ground. This example is just an introduction to the world of relative motion and reference frames. Welcome to this interesting world.
Okay, I think we're done with that. Now, before we go to projectiles for today, I want us to. Oh, sorry about that. Can you hear me now? Aha. So I said, I guess we're done with that. So now, before we go to projectiles, I just want us to do a little quiz based on laws of motion, okay? Yeah, just hold on. We're going to do a short quiz. Just hold on. So, right now to the quiz, here comes the question for Daniel. What's your option? Read the question out and pick your answer. Daniel, read.
What is the push or pull of an object?
What's your answer?
Force.
Force. That's correct. So the next person, Festus. Read.
It has already see, why not? Side has cut. He said you read it.
Why is it harder for the boy in image B to get down the hill? Friction. That's correct. The next person, if these boys are pulling with the same amount of force, what will happen? If these boys are pulling with the same amount of force, what will happen? What did you say? Eh. What is the answer?
They will not move at all.
Because yes, because it's equal. Yeah, equal amounts of forces. Take note of that. Next person. Which force produces a change in motion? Are you sure it's unbalanced force? Okay. Please concentrate. Next person. At which point is potential energy greatest? Is it W? Is it X? Is it Y or Z? Let the owner of the question answer. Yes, what is the answer? W. That's correct. Now, who is the next person? Okay. Read the question, let me hear you.
It takes more force to accelerate the Iron Man on the left than the. That's called. I cannot see the question.
Okay, let me read it for you. Please, I want you to keep quiet, please. It takes more force to accelerate the Iron Man on the left than the Iron Man on the right because the Iron Man on the left has more mass. This best describes dash.
Defines that. It takes more force.
So, is it Newton's first law of motion, which is the law of inertia, or the second law of motion, the law of acceleration, the third law of motion, the law of reaction, or the law of universal gravitation. Which one?
Second law.
Second law? Well, that's correct. Okay. Whether she was not sure or not, she gets it. Now, Daniel, the formula mass times acceleration, or MA, is used to find what? Force. That's correct. Festus. Festus. For every action, there is an equal and opposite reaction. Which option?
Third law.
Third law. Third law, that's correct. An automobile you are riding suddenly stops and you continue to go forward. Which law? Who is answering? You said first law, right? That's correct. Action, reaction. Which law? Third law. That's correct. Look at this. Different material with the same force. One moves while the other was reluctant to move. Different material. The black and the white material, different material with the same force. One moves far, the other was reluctant to move. Which of the law does it describe?
Second.
Are you sure? One more chance.
Okay.
You know, the one that was reluctant was because of its material, right?
Yes, sir.
And it's the same force that was applied to the two. But one, just like there is air in a cylinder and there is air in a balloon, you tap the balloon, it jumps away. But you tap the cylinder, it did not move far. First law. Oh, second, right? You are right. Second. Okay. Let's go ahead. Now look at this one. The vehicle suddenly stopped, but you keep moving at the initial speed of the vehicle. Which law?
Second law.
I'm the one asking the
The
question.
vehicle suddenly stopped, but you keep moving at the initial speed of the vehicle.
That's third law.
Are you sure?
Yes, sir.
You know, you continue to move because you do not want to stop.
Second law. Third law.
No, you continue to move because you do not want to stop. Okay. One object has twice as much as mass as another object. The first object also has twice as much dash. One object has twice as much mass as another object. The first object also has twice as much dash.
Don't do fast.
Daniel,
Your question. Daniel.
Look for one word that can replace mass. Look for one word here that can replace the mass. What did you say? Inertia. Inertia, that's correct. Festus. What is the attractive force that exists between all objects that have mass? Gravity. That's correct. If an object is stationary, the forces acting upon it are dash. Balanced. When a cannon fires a cannonball, we observe Newton's third law. Which force is the reaction force? It fires the ball forward. So what will happen to the cannon? Are you sure? Not the cannonball. The cannon itself, what will happen to it?
Because the force that is used to release the cannon.
Yeah, it will move backward.
I got it.
What law does this picture represent? When you match the brake, you jack forward. Which law? First law. Okay. I think first law. What did you say? Newton's third law of motion states that what? For every action, there is an equal but opposite reaction, right? Okay. Let somebody answer this question. What do each of these letters correctly represent? All right. Just said somebody. Okay. All right. Yes. Force, mass, and acceleration. Okay. Finally, anybody?
Gravity.
That's magnet.
Another option.
It's magnet.
Another option.
Magnetic. Friction. It's magnetic.
Is friction.
Friction, I got it.
You know, magnet can pull an object without touching it. Yes or no?
Yes.
It can pull an object without, but friction, it has to contact, okay?
Yes, sir.
All right. We're going to move to projectile now. Just hold on a bit, okay? Hold on a little bit. The question they may ask you, what is, when you say what is a projectile? You can write it down while I'm going to explain along. A projectile is an object. You can write, okay?
Yes, sir.
That is propelled by an initial force and then continues to move under the sole influence
What's this?
Okay.
9, Wednesday. 12.
Under the sole influence of gravity. For example, if you have a cliff, let's say this is a cliff, and from the top of a cliff, you want to project a particle. You want to project this particle from the top of the cliff. As you project the particle, it has a tendency to go along the horizontal path, okay? It has the tendency to follow this path. So as you project or propel the object or the projectile, this is the path in which it's supposed to go. But because we have gravity, it will never go in this path. Because of gravity, it will never go in this path. It might tend to follow the path initially, but then it's going to move down, until it reaches somewhere here. Then it might follow this path. Do you understand now? Do you understand this? So instead of going in a straight line horizontally, because gravitational pull is acting on it towards the earth, then it will keep going, along this path until the object that was initially at the top would have landed here. Is that clear?
Yes,
So
sir.
if it is not totally controlled by gravity after it has been in motion, then it is not a projectile. Take note of that. So are you through with the notes?
Yes, sir.
Yes.
You're
No.
through, you're through with the notes, right?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So did you say you are not through?
Yes, sir. The drawing.
Okay, okay, okay.
Yes.
So once you are through, you let me know. Can you hear me now? So examples include a thrown baseball, a thrown object, a thrown baseball. Let me write that thrown again. So a thrown baseball, okay? Then, or we can say a kicked football. A kicked football. can be an example, or you can even say, why am I using capital? So you can even say a bullet fired from a gun. So these are examples of projectile motions or particles. Now, once an object becomes a projectile, once an object, I need to write this, becomes a projectile, like I mentioned before, its part, its part, the part which is called trajectory, so its part called trajectory is a curve.
Yes, sir. I'm getting you the case, sir.
Okay. So its
I
part.
cannot see that face.
Okay, you cannot see towards the hand there.
We can't see.
Okay, hold on. Can you see it now? Can you see it now?
Yes, sir.
Okay. So its curve, its part called
Yes.
trajectory is a curve. So let's take note of that. And it's usually a parabola. Usually a parabola, and its motion can be analyzed by breaking it into independent so by breaking it into independent horizontal and vertical components. So once an object becomes a projectile, it will go in a parabola path, which can be analyzed into both horizontal and vertical components. Is that clear? Is that clear now? Okay, when you are through, you let me know. Then I will analyze the motion under here. Yes, when you are through, you let. Are you done?
Yeah.
Okay, you are finished, right?
Yes, sir.
Okay, fine.
Yes,
Now,
sir.
this is a projectile motion. Look at this carefully. This is the starting point of this projection, okay? You can see the particle that is being projected. It moves to the end where it stops. As it was going up, but not directly up. Why is it not going directly up? That is because it was projected at an angle to the horizontal. It was projected at what? At an angle to the horizontal. What will happen if it was projected at 90 degrees? Had it been it was projected at 90 degrees, it will not go this way. It will go vertically upward. Is that clear? So at every point of the journey, we have several points here. Point 1, point 2, point 3, and point 4. We could identify more than 4 points, but we want to reference 4 points. Okay? So at point 1, the total velocity will be a factor of the initial velocity u cos theta and a factor of gravitational influence u sin theta. Because it's going up, gravitational influence is pulling it downward back. But because the velocity is much, it did not go back immediately until it reached a point when it can no longer go, forward. Then the height will return to zero. It cannot increase the vertical distance again. That's why it will return to zero here, because the velocity that it was using has finished. Then it will now start coming down under the influence of gravity. At this point, gravity is working on it, pulling it downward. Is that clear now? So the point O is called the point of projection. Theta is the angle of projection. And the distance OB is called range. Horizontal range, or simply range. Distance from starting point to the stopping point. That's the range. Then the total time taken will be the time it takes from the particle to fly from starting point to the ending point. So if you know the time it takes to get to the maximum height, this place is maximum height. So if you know the time it takes to get to maximum height, then you can multiply the time by 2, because it takes the same time to go downward to get the total time of flight. Okay, let us put down some terms associated with projectile. Okay, terms associated with projectile motion. You can write so. The terms associated with projectile motion include trajectory. What did I call it? Trajectory. This thing is lagging a bit. So what is the first term? Trajectory. So this is the curved part this is the curved path a projectile follows through space. So that curved path is called trajectory or trajectory. So the second term is velocity. So velocity, this includes the speed and the direction of the projectile. The speed, let me write that again to write it here again. And the direction of the projectile. So that is what the velocity is talking about. So this is often broken down into the horizontal Vx or Ux and the vertical Uy components. So that is Ux equal to horizontal component of the velocity while Uy equal to vertical component of the velocity. Then the next term that we want to mention is acceleration. So acceleration, this is the rate of change of velocity. So the rate of change of velocity, that is acceleration. In projectile motion, acceleration due to gravity is what we usually consider. Yeah, let me write it at this place. So acceleration G due to gravity equal 9.8 meters per second square. Then the next thing is the angle of projection. Angle theta of projection. The angle of projection. This is the angle at which the projectile is launched. This is the angle at which the projectile is launched. So that is the angle of projection. Then we have more things to talk about. Are you through with this? The next thing is range.
No, sir. I know where I
Range is a distance. This is the total horizontal distance. The total horizontal distance. That's along the x-axis
Festus and
that the projectile travels before returning to the ground. Before hitting the ground. So that is the range. Then the next thing to talk about is the time of flight. Time of flight, when you project something, it will fly and then drop. So this is the total amount of time the projectile is in the air. This is the total amount of time the projectile is in the air. That is total time of the journey, total time of flight. Then we have what is called maximum height. Maximum height. This is the highest point the projectile reaches in its trajectory. That is along its path. Once you finish, you let me know. Thing to boost your understanding of this topic, okay? Make sure you are attentive now. We want to do a kind of a little practical on projectiles. Are you ready now? Before we round up, we want to do a little practical. Are you ready?
Yes,
Don't miss out of the practical. If you miss it, you're on your own, okay? Make sure you focus. Make sure you focus. Somebody is not focusing here. Now, look at this. Can you see the black particle on the board?
yes,
We want to project the black particle at certain angle. Daniel, what angle do you want to project your projectile? Give me one angle. between 0 and 90.
Sir, 90 degree.
90-degree, right?
90 degree.
Now listen. If I show you 90-degree, you know what it means, right?
Yes, sir.
Can you see this shape?
Yes, sir.
So if you must project your particle along 90-degree, can you see this particle here?
Yes, sir.
If you project it along 90-degree, where do you think it will go, Daniel? Will it go up or will it go like this?
Oh, that's 90 degree.
It will go up and come down the same way, yes or no?
Yes, sir.
Then it will not give you proper projectile. It will not give you the parabola, right?
Yes.
Then you will not be able to find your range. You will not be able to find, all of the components there. The only thing you can talk about here is maximum height that it will reach and it will come down.
Yes, sir.
So pick angle between 0 and 90. 0 and 90 not included. Daniel. Daniel, give me another angle.
Sir, this is angle.
Yeah, give me another angle.
Sir. Sir, this is angle.
Give me another angle. Mention another angle.
60 degree.
60 degrees. Can you see me changing the angle?
60.
Can you see me changing the angle?
60 degree.
I'm only asking question. All of
Yes,
you.
sir.
Can you see me changing the angle? Somebody is putting
Yes,
the head on
sir. Sir, we are talking is the connection.
the table. I want you to observe what I'm doing here. So, what angle is it right now?
55.
So you said 60, right? Daniel, what speed do you want your projectile to have? Give me speed between 0 and 60. Give your projectile a certain speed. 30 meters per second, right?
Sir, 50.
You said 50 meters per second, right?
Sir, 30.
Did you say 30?
30, 3 and 0.
Okay.
Yes, sir.
At what height do you want to project your projectile? Is it at 0 or give me from 0 to 120?
Sir, 90.
90 meters. So I will project it now and you will see, right? Are you ready to watch it?
Yes.
1,
Yes, sir.
2, 3, go. Can you see it?
Sir, it's angry.
No, it has finished now. Okay, now let me show you again. Still the same dimension. Now watch it. Can you see that? So now let's see. I want to take this to the board. Then we will now try another one, okay? Is that clear? So on the board, this is for Daniel, right?
Yes, sir.
Remember, you can project even at zero height. Not compulsory you go to a certain height, okay? Like when you want to kick a football, you kick it from the ground, yes or no?
Yes.
So the next person should consider that before you make your choice. I am not saying, Festus, what arrangement do you want for your projectile? What is the speed? What is the angle? And what is the height you want?
The height should be zero.
Should be zero. Like you want to kick a football, that's good. Any other, the angle and the speed.
The speed should be 50.
50 meters per second. What about the angle?
30.
Okay, imagine you want to kick a football at 30 degrees. How far will it go? Or, how far? That's the range, right? How far it will go? That's the range, yes or no? Let me show you again. Can you see this? Can you see this? Can you see
Yes,
this?
sir.
Okay. Now, if you kick the football at that angle, it will move forward. So let's go and do it now. We shall start it now. Are you ready? 1, 2. Watch it at the top. You see that it is at 0 seconds at the top, okay? But for Daniel's case, what is the time of flight for Daniel? Anybody?
1.691
Seconds. Again?
7.691 seconds.
Good. What is the range? What is the horizontal distance that Daniel's particle travel?
115.6 meters.
Yes, 115.36 meters. Okay, and that was because Daniel projected at 90-meter height, right?
Yes,
So,
sir.
Festus, you can use this to determine whether when you kick it, it's going to enter the goalpost on the next. So let's start. 1, ready, go. Now, this is the analysis or the result from Festus' attempt. Okay? So let somebody check what is the time of flight?
5.103 seconds.
Seconds. Good. What is the range?
The range is 220.93 meters.
So that means if you kick a football with the conditions of 50 meter per second velocity, 50 meter per second velocity at 30 degrees, then it's going to cover this range in 5 seconds. Okay? Is that clear?
Yes, sir.
This is projectile. So who's the next person?
Boluwatife.
Now give me your parameters quickly.
Bolu.
Give me your parameters. What height do you want? 20. At what angle? 60.
Yes, sir.
What speed do you want? What speed?
45.
45.
45.
Did you?
45.
45, okay. Now let's watch it. Can you see it?
Yes, sir.
So what time? What is the time of flight?
8.438 seconds.
What is the range?
The range is 189.84 meters.
So you know these are various questions that you might be given in exam, and they will ask you to calculate the time of flight, to calculate the range. Okay. Who is the next person?
Rejoice.
Oh yeah, Rejoice. What are your parameters? Do you want 0? Do you want
60.
60? What is the degree you want? 60.
Yes, sir.
What is the speed you want? 60. Can you see it? It's interesting, yes or no? All right. What is the range?
349.66 meters.
So it went so far. Now, what is the time of flight?
11.656 seconds.
Okay. So you can see this, right?
Yes, sir.
Okay. Who is the next before we round up? Okay. What are your parameters quickly?
120.
Which one?
Height 120.
Height of 120, okay, yes.
Yes.
Angle,
90.
well, we said we should not use 90 because it will just go up and down, that's all.
That is what's the highest time?
Just put
Choose below 90. Okay, 89, right?
Sir, use 85.
85.
Yes, sir.
85 is close to vertical. Let's use it. Let's see. What is the speed? Highest speed?
It's only one when I say.
she's the one that is. She's now.
58.
45.
45. Then it will not. Well, let's see.
He's going to go for that.
So,
Jesus.
okay. Remain one person, right?
Yes, sir.
So after the one person, we are going to round up so that we can have SS2.
Okay, sir.
Okay, sir.
So,
You said after the.
After the last one.
now,
Yeah.
the last person, what are your parameters?
Height 120.
120,
Angle 60.
60.
Okay.
Speed.
Speed 90.
90.
60, there's no 90.
Oh, we have 60 as the maximum here. So I should use the maximum speed, right?
Okay. The angle 120.
90.
No, angle must be below 90.
90.
Angle must be below 90. 90 is just straight line up and down. It will not even reflect.
That's 60.
That's 60.
Then the speed, is the speed also 60?
It's okay. So it's okay like this.
All right, all right. Can you see that? So what is the range?
376.65 meters.
What is the the time of flight?
12.555 seconds.
Okay, so that is where we'll be rounding up your class for today, okay? All right. Can you hear me now?
Yes, sir.
So we have come to the end of your own class. You can let your SS2 come over, okay? Goodbye.
Bye, sir.
Goodbye. See you.
Goodbye, sir.
All right. So viewers, thanks so much for watching. You can subscribe to this channel for updates on our future. Bye.